All right, so recording has started. So last time we were doing this substitution, integration by substitution, and this is the criteria to use. So we look for any composition functions f of gx within the integrand for which the substitution produces an integral which can be expressed entirely as a function of u. So basically, what we do is we look for something, uh, some composition function f of gx, and because if I take u as gx, then the differential of u can be written as the derivative of gx with the differential of x. So it means I need this derivative with dx. So it means I need g prime of x with dx. If this whole thing is given in the integral, then we can easily replace this u as gx, and because the derivative of this whole thing becomes du, so you see your function will not have any x in it, and the whole integration will be converted to u from x. So we look for a part of a function. It may not be a complete function, but a part of a function whose derivative is given with dx. So this was the section 5.3, I think. Is it 3 or 2? 5.3, integration by substitution. And we did many questions um, last time. So for example, I can try this one. Uh, Integration of sine square x into cosine x dx. And here you see sine is the derivative of cos and cos is the derivative of sine. But sine is within the power. This is not alone. So it means this should not be treated as a derivative. Cosine x should be treated as a derivative because that is alone. I don't want g prime x to be inside some function. It should be alone with d of x. It should not be in any other function. You see, gx can be in some function. I think anyone can accept the requests, right? Or only me? All right, so I will keep doing that. So see here, if we have, if I substitute, this is called a substitution. So if I let or substitute u is equal to sine x only, not with the power, just inside. You see, I am not taking the full f of g of x as u. I'm only taking the inside function, this gx as u. So outside function f remains there. So here outside function f is the square. See, it is the square of sine x, right? So f is the power and gx is the sine. So we can just take u as sine x, and the differential of u will become the derivative of sine x with dx, differential of x. So now you see this whole thing has become du. This whole thing has become du, and sine square. This sine square has become u square, and I think I can just write it here. This has become du. So my integral has been converted to u by this given substitution. So now we know that the integral of u square is just u3 by 3 because these both are the same. It is the variable u and d is also with respect to u. So if these variables are the same, I can use the formula for integration. And now, because my question is in x, my answer should also be in x. So I can replace my u back. U is sine. So I just replaced this u by sine x, right? And square will remain there, power 3 will remain there, plus c. And we know we can write sine cube x. Sine to the power 3 means sine 3x plus c. So that is the answer. All right. So it's easy, not very difficult. If you look at example 8 on page 336, it is ex by x. Another example is given. Integration of e to the power square root of x and divided by square root of x. Now you can say that where is the function? The composition is e to the power. See, f of g of x here is e to the power square root of x. This is so I have to pick some gx from there. It means I can take the power as u. I can take the power as u. But the derivative of this power is 1 over square root of x. So see, 1 over square root of x is given. So maybe I can rewrite it as integral of e to the power square root of x separately, and I can write 1 over square root of x dx separately. Because it's not a problem. If a and b are divided, I can write it as a into 1 over b. So that's what I did. Now we know that this is some kind of the derivative of the power here. See, 2 will be missing. The derivative is 1 over 2 square root of x. But constant is not a problem. As long as the variable part is given, we don't have any issue. So I can substitute. This is a side. I am just explaining these things to you. No need to write that. So I can substitute u as just the power of exponential function. And the derivative or differential of u will become the derivative of square root is 1 over 2 square root of x dx. But because here I don't have any 2. So if 2 is not there, I can just multiply it over on the other side. So I can write 2 du is equal to 1 over x dx, because in the integral I am only given 1 over x dx. So now you can see that I can write e to the power becomes u, and 1 over dx, this becomes 2 times du. It's not just du now, it's 2 times du. 2 is a constant. I can bring it outside. So I can write 2 e to the power u and with respect to u. So now you see how easy this integral has become. We all know that the integral of the exponential function is the same. Integration of eu is the same as e to the power u. And at the end, I will just replace the power u. U is square root of x, so I just replaced. 2 is there. So see, I have this power, so I replaced this power. So at the end, don't forget this last step. So see, again, going back to the question, look for something whose derivative is given with dx. Okay, so see, I looked for something whose derivative was given. You see, d by dx, not integral, whose derivative is given with dx. And you can say that derivative is 1 over 2 square root of x. But as long as the variable part is given, we are okay. Because constants can be adjusted, variables cannot be adjusted. So 2 was missing, so I got an extra 2 here. But no problem, I can just bring it outside. Excuse me. So C2 is written outside. That's why I said constants don't matter. Constants can be adjusted. Some substitutions. Some substitutions will not be very straightforward. For example, I have a question cosine cube of x dx. That's it. You see, if this question has a sine x with it, let's say, if this question has a sine x with it, it's very easy because the derivative of cosine is sine. So I can simply take u is equal to cosine x. Derivative will become minus sine x dx. Minus is not there, but we don't care about minus because minus will go to the other side. It's a constant, minus 1. So see, I can write this as u to the power 3 into minus du, because this whole thing becomes minus du. So it's very easy. You can bring minus outside and write u cube du. It becomes u4 by 4 plus c, and you can put u4 as cosine 4x plus c. So just by having this sine x here, things have become very easy. Let's say if this 3x is missing, I wanted to write this example actually, but I wrote the simpler one before. So let's say if you just have cosine cube x and no sine x is given. This can be a challenge now. This is not very obvious. So here, if we think about a little bit about trigonometry, you can write this as cosine square x into cosine x dx. Let's say I split it. We can do that, right? Because if you have any power 3, we can write it as x square into x. So I wrote cos cube as cos square into 1 cos. But cos is the derivative of sine, not cos. If I take cos as u, it is not the derivative of cosine x. It means I need this function to be converted into sine x, because the derivative of sine x is cosine x. So cos x dx remains there. I know that sine square x plus cos square x is 1. So from here, I can write cos square x as 1 minus sine square x. So using this formula, I converted my function to sine x. And now you see here, sine x is there and the derivative of cos x is also there. So it means I can use substitution u is equal to sine x. So du will become cosine x dx. So see, this substitution was not that straightforward. So you got 1 minus, the substitution gives you 1 remains 1, sine square becomes u square, and this outside cos x dx becomes du. So see, now it is integrable because the integral of 1 is u and minus integral of u square is u cube by 3 plus a constant of integration. So if you have, now I can replace u is equal to sine x, and u cube will become sine cube x by 3 plus a constant. So this substitution was not that straightforward. We had to manipulate a little bit the trigonometric function cos cube. This can be done with any odd power, not just cos cube. If any odd power of sine or cosine is given, this technique can be used. You see, whenever, let's say if you have sine to the power 5x, let's say dx, you have this example. Okay, now because it's an odd power, I can write sine 4x into sine x. Now sine 4x can be written sine square x to the power 2. Sine square x to the power 2 into sine x. And because sine square can be converted to 1 minus cos square x now, and power 2 will remain there, and sine x dx. That's why I said odd power. If this power is odd, we are okay. If this is odd power, we can always do that. Because when I split an odd power, if A has an odd power, and if I split 1A, the remaining power will become even. And even power can be written as A square to the power. Here, even power can always be written as the power of a square, because I need sine square or cos square here, so that I can write it as 1 minus sine square or 1 minus cos square. So power now will remain there. If it is sine 7 will become cos sine 6 into sine, and sine 6 can be written as sine 2 to the power 3. Okay, so that's why odd power is okay. But if even power is given, I will not split it. If sine 4x is given, and if I split it, it becomes sine 3 into 3. And sine 3 into 3 is not good, because sine 3 into 1, I have to split one power separately with dx every time. And if it is an even power, this will become odd. If this is odd, I cannot write it as a power of 2. So now if I use the substitution, u is equal to sine cos x, right? Now cos x has the derivative sign. So I will replace cos x as u, and then minus sine x dx will become uh, du, and I can bring minus du on the other side. So I got a 1 minus u square whole square into minus du. So now I cannot integrate it directly because it's 1 minus u square and the whole power 2. So I have to open up the power. So a square minus 2ab plus b square. And this minus sign, I can write it outside and then d. And now we can integrate it, no issues. 1 becomes u, 2u becomes 2u cubed by 3, and u4 becomes u5 by 5. Plus a constant of integration, and now you can replace your sign back. So minus sine x plus 2 by 3 sine cube x minus 1 by 5 sine 5x plus constant. I brought this minus inside. That's why this becomes minus, this becomes plus, and this becomes minus. All right. So if you have odd power of sine and cosine, any power, any odd power of sine and cosine, this is doable. But if it is even power, then it's difficult. Even power is not that easy. Okay. So what we do with even powers, I can at least give you sine square and cos square formulas. Sine square x dx and cos square x dx. Here, if you split it, it does not work. This splitting will not work here for odd. Splitting won't work, right? Reason is that if you split even power, if you have a to the power even, if you split, it becomes a to the power odd into a. So this odd, if you write this 2 and the power, this power will become a fraction because that odd number will be divided by 2. So it will become either 3 by 2, 5 by 2, 1 by 2. So we got a power which is square root or cube root square, like that. So this will not be handled. We cannot handle this type of power. So that's why uh, for odd powers, at least for even powers, I have something to do. What is that? Uh, for even power, I have half angle formulas. They call it 1 minus cosine 2x by 2. And cosine square x is 1 plus cosine 2x by 2. Same formula, only minus plus difference. Both for sine and cosine, we have cos 2x on the right side. But sine has a minus and cos has a plus. These are called half angle formulas, I guess. These are called half angle formulas. If you Google it, if you write half angle formula in Google, you will see these. So whenever they give you, let's say, sine square x dx, you don't split, you write 1 minus cos 2x by 2 dx. Now 1 by 2 is a constant. I can bring it outside. So it will become 1 minus cos 2x dx. So here 1 has the answer. 1 is x, but cos 2x has no answer because I know what is cos x. I don't know what is cos 2x. So here I can use the substitution 2x. I can call it u. You can call u as 2x. Du will become 2 into dx. 2 can come down from here. So dx becomes, so 1 by 2. This becomes cosine u into du by 2. So I have x by 2 minus this 2 will come out and it will become 1 by 4. And now cos integral of cos u is sine u plus c. Agree? And now you can replace your u back. So you got x by 4 minus sine u is just 2x by 4 plus c. So that's how you can do a sine square. And if it is cosine square, only plus will come here, right? Only plus will come here if you have cosine. If this is cosine square x, you have just plus here, plus here, plus here. That's the only difference in your answer. This will be the only difference in your answer. So both sine square, cos square has the same technique. All right, so let's see what else we have in this section. I did few problems from this example is here, cos cube x that I did. So we did quite a lot from here. So here in first 12 questions, they gave you the substitutions. All the substitutions were given, and that's why this was a little easier. And after that, substitutions were not given. And we tried some from here as well. I can e to the power. So we can do some from here, maybe 16th problem. Then, so here you see, I can write something here or not? No. This is a highlighter. There is no we can do this one. Or maybe 25, 31, 33. This 30th may be better. So let's say if I do 16th problem, x cube 5 plus x4. Exercise. This is now exercise 5.3, exercise number 16. So this was x3 into 5 plus x4 dx. So now if we look at this one, this 5 plus x4, actually x4 has the derivative x cube, but 5 has derivative 0. So why not include it? So if I take u is equal to 5 plus x4, do not take the square root. I saw students, they take the square root with it. No, we cannot handle it if you take the square root. Just take the inside function only. So du will become 5 is 0. So it becomes 4x cubed dx. So I can divide by 4. So du by 4 will become x cubed dx. Why I wrote it like that? Because I have x cubed. So see, I can rearrange the terms. 5 plus x4 and x cubed dx, I can write it together because x cube and dx can be written together. They are multiplying, so we can write them like this. Now, inside the square root is there. 5 plus x4 becomes u, and x cube dx becomes du by 4. Right? So I got these answers. So see this one, this inside thing has become u. Okay? And this one is du by 4. So now if you write 1 over 4 outside, because 1 over 4 is a constant, and square root means 1 over 2 du. Square root of u means u 1 by 2. So 1 by 2 means u to the power 1 by 2 plus 1 over 1 by 2 plus 1 plus a constant of integration. So that becomes 3 by 2. So u to the power 3 by 2. You can directly write 3 by 2. If you know 1 plus 1 half is 3 by 2, we can directly write this. And here 2 can be cancelled with this 2. So I got 6. 1 over 6. And u was 5 plus x4. So we can replace u back, power 3 by 2 plus c. So that's the answer. We replaced this u back. You see here, this was the u. So I replaced the value of u back here, 5 plus x4. And then it was, I said we can do, this is also the same thing. 7t square plus 12, the derivative is 14t. So t is given outside, so no issues here, right? So if you take this as u, this derivative is t. 24 is 1 plus 16x squared. 24 is 1 plus 16x squared. So here we know that we have a formula 1 over 1 plus u square. If I just have 1 over 1 plus u square, it is tangent inverse u plus a constant. This is formula from the table. So it means I just need one u here, just u square, 1 plus u square. That's what I need. And that goes here, red with red. So it means I can write this as a square, right? I should write this as a square. So it means I can take u as 4x. 4x, not 16x. If I take u as 4x, then you see u square will become 16x square. So this will become my u square. This will become u square. That's what I need. But now I cannot just write that. I need from here, I need du as well. So du is just 4dx. I don't need 4 here. So I can divide it on the other side. So this has become 1 over 1 plus u square, and dx is du by 4. This dx has become du by 4. So now 1 over 4 is outside, it's a constant. So 1 over u square du, that is tangent inverse of x. So that becomes tangent inverse of u plus c. I use this formula. So now at the end, of course, we have to replace u back. So u is 4x plus c. This one, x square e to the power minus 2x cube, 33. X square into e to the power minus 2x cube. Now you see if I rearrange the terms, if I write e to the power minus 2x cubed first and then x square dx, now you can see that the power has the derivative square. There will be a constant, but square will be there, right? So it means I can take the power, the whole power minus 2x cubed as u, and du becomes minus 6x square dx. So I can divide 6 on the other side. That will become minus 1 by 6x squared dx. Now I have everything. So I can write e to the power u, and this whole thing becomes du by 6 minus. And put a bracket because minus is not, it's not eu minus du by 6. We are not subtracting. We are multiplying by minus du by 6. We have to be careful, okay? So minus 1 by 6 can be written outside now. Minus 1 by 6 is constant. And inside, I just have EUD. So now here, I got the same integration. EU has the same integration. Now at the end, I can replace the value. So minus 1 by 6. E to the power u. U is minus 2x cubed plus c. So this is something which we did before. So if I go ahead, remember all these integrals in 5.2 when we started this. This was called the indefinite integral. I never called it indefinite. We said I am just calling it the integral, the integral, the integral. That's it. The integral of fx with respect to x. So what is this indefinite? The full name is indefinite integral. Basically, we have another integral which is called the definite integral. That's why this simple integral, the antiderivative, the indefinite integral is just the antiderivative, basically, the inverse of the derivative. But the indefinite integral is not the antiderivative. Indefinite integral is defined separately. This indefinite integral is basically integration of fx dx over some interval. So we write the interval a to b. These are called the limits. So basically we are integrating something over a given interval of values, a to b. So this is a given interval, a to b. And if any function is continuous function, y is equal to f of x, continuous function on there, this integral is used to find the area under the curve between the graph A and B above the x-axis. So this area is basically given by this integral. It will be a number. Area is a number, right? Area is not a function. So antiderivative was a function of x plus a constant of integration. But this is a number. The answer to this definite integral will be a number. The definition of this integral is this one. If you remember when I started this course calculus, I said we have two geometrical problems. One problem was finding the tangent line at a point, right? And the second was finding the area under the curve. I said finding the tangent line is your differential calculus, which we get from chapter 2, 3, 4, right? And the second problem, so this is done already in derivative, chapter 2, right? We did it. Now in chapter 5, we have this answer to the second question. If y is equal to fx is given, how to find the area under this curve between the points A and B, this area, how to find this area. This area problem is the second one, which we will do it now, which is given by integral calculus. Uh, Basically, the idea is I will not ask you this idea. I will just ask you this definite integral, and you will see that the definite integral is very easy. The idea is we divide our interval into many sub-intervals like that, let's say, and we draw lines like that. And now at the top of each line, each interval, we replace this curve by a straight line like that. We replace this curve by straight lines like that. Okay. So see, if I pick one of them, let's say if I pick one of them, this was my curve is going like that. But what I did a straight line like that. So actual area is under this curve. Actual area is this one, right? Under this curve. But what I did, I got the area of this red one. So it means I am getting some extra area here. You see, I'm getting some extra area which is not the part of my area, but I am losing this one. Sorry, this is not extra. This is the extra. So I am gaining some extra area here. You see, did I gain this or lose? I lose this. This is something which I am losing, and this is something which I am gaining, right? So this red portion is the extra area that was not needed and I got it. This one, right? And this was needed and I did not get it. So we hope that when we compare, both areas will give me almost the same answer. And we are not doing it just at one place. You see here, we are getting extra area, we are losing some area. We are getting extra area, losing some area, extra area, losing. So at each portion, we are gaining and losing, gaining and losing, gaining and losing. So if I add up all these areas, area of this, area of this, area of this, area of this, if I add up all these areas, we say that, okay, then area of rectangles. Basically, these are the areas of rectangles. When I make a straight line at the top, it becomes a rectangle. And we know how to find the area of a rectangle, length into width. So if I add all the areas of these rectangles, area of rectangles, right? And this will, if you give up, if you add up, get all the area, this actually gives you the approximate area under the curve, actual area, right? We call it area under the curve. So this is basically the idea. So what they say if you pick any point here, any point, let's say x1, x2, x3 in each interval, then the height of the rectangle is f of x1, f of x2, f of x3, so on. So the area of first rectangle will be the width of the height of the rectangle and the width of the rectangle, right? So we call it delta. Delta is the width of each rectangle. This width is delta, first area, and the height comes from the function fx1. So if you keep on adding f of x2 delta x2, f of x3 delta x3, these are the areas of all rectangles. Okay, this is the sum. This is called, the name of this is Riemann sum. Riemann was the name of some mathematician who got this sum, who got this idea. But this is also defined as the definite integral. If you take the limit, if you take the limit as n goes to infinity, this gives you the actual area. It will not be, your area is approximately equal to this one. Okay, approximate area. But if you take infinite many rectangles, take infinite many rectangles, then this area will be exactly the sum of rectangles. But you know that we cannot add infinite many rectangles. We can just increase 10, 20, 30, 40. So the more rectangles you take, the more accurate area you will get. Okay. The right hand side, which we wrote the Riemann sum, this is actually the definite integral. What we wrote on the right side, this is known as the definite integral of fx with respect to x. So that's why we said that this gives you the area under the curve. So this is a formula, but I cannot find this sum. Finding this Riemann sum is not easy. Okay, this is given in section 5.4, but we will leave it. I will not do 5.4. It's a difficult thing. So I can go to section 5.5 and 5.6 together. In 5.5, 5.6, they give us some properties of this. They say if you go from A to B, fx dx, or if you go from B to A, let's say B to A, then I can write it as minus A to B, fx dx. Means if I change the limits of integration, okay, these are called, let me first write, these A and B are, A is called the upper limit of integration, and this is called lower limit, because so lower limit is always smaller than the upper limit. Okay, so A is always less than B because it's an interval. The left side is always smaller, and am I back on? This is one of the properties. These are given in section 5.5. Another property, they say if you go from A to A, if the limits of integration are the same, it means you don't cover any area. It will always be zero. Okay. So if you have not started walking, you are not covering any distance. So it's zero. So then if you go from A to B dx, and if you want to stop in between, let's say you say, okay, let me stop at C. Okay. And then start from C and go to B. So no issues. You can add them. So C is between, where C is between A and B. If you want to take a stop between A and B, you go from A to C and then go from C to B and add them. No issues. It gives you the same area. See, from A to C and then from C to B. So if you add these two areas, of course, it gives you the total area from A to B. So you can take stop between. This is what basically means. And in 5.6, basically we are doing 5.6. That is more important. In 5.6, we are given a fundamental theorem which will make our life very easy. It will give you the answer to the definite integral. They call it fundamental theorem of calculus. What is that? It says that if capital Fx is any antiderivative of small fx, means the integral, right, of small fx, then your integral from A to B small fx dx, basically they said find the antiderivative of x, because you see the integrals, we are using integral sign, so it means it has something to do with the integral. So we got the integral, This is fx. But now limits are given. So this should not be my answer. You see, if limits are not given, if fx, capital Fx is the antiderivative, this is my answer, right? This is what we studied in 5.2, that if fx, capital Fx is the antiderivative of small fx, then we can write it like that. But if limits from a to b are given, I don't need a c here. No need of c. Just pick fx and use the limits. We write limits like that because integral is done. Integration is done. I cannot use this sign anymore, right? But I still have something to do with limits. So we just put a slash, or sometime we put this big bracket. We said that, okay, we got this function, but now I have to use the limit. So we use big brackets and we write AB at that. Both notations are used. But what does it mean? It means first put the value B for X and then put the value A for X. And this is plus and this is minus. It means you have to put uh, B first and then minus put A for X. And this is a number. You see, the answer is a number. That's what I claimed, right? That's why it gives you the area. Okay, so this gives you the definite integral. And here one condition is that, remember, fx needs to be a continuous function. Needs to be a continuous function. There should be no break. You see, in chapter 1 we studied it needs to be continuous on the interval, on the interval a to b. If it is not continuous on the interval a to b, I cannot use this theorem. Remember. So continuity is very important. If it is not continuous, the problem is there is a break. Let's say if there is a break, right, and you are going from a to b, something will be missing. You see, the area will become infinite. At this point, it is going to infinity. Okay. So let's say if there is a discontinuity at some point C, what I will do, I will break my interval into two parts. You see, I had a property. If there is a jump discontinuity, not infinite. If there is a jump discontinuity means like that. You have a stop here and you take a jump and start from there. It means it is not discontinuity like that going to infinity. Not like this. This is fine. This is called jump discontinuity. If some function goes to minus infinity or plus infinity, that is not called it. Infinite jump is not acceptable. If that is the case, I will break. I will go from A to C and then go from C to B and get the answer. I will use that property, right? If there is a jump discontinuity, we can use this property that I wrote here, third property. So let's see if I write 1 to 2 x square dx. Now you see, from 1 to 2 x square is fine. It's continuous everywhere. Okay. So what I can do, first I will take the antiderivative of this. What is the antiderivative? X cubed by 3. And then I will use the limits from 1 to 2. So it means I will replace 2 inside. So 2 to the power 3 by 3. And then I will replace 1 for x. So 1 to the power 3 by 3. Okay. So here I replaced this. I replaced this x by 2 and by 3. By this number 2 and by this number 1. Sorry, not 3, 1. Right? 1 cube, 2 cube minus 1 cube. So that becomes 8 by 3 minus 1 by 3 is 7 by 3. So see, 7 by 3 is a number. And you see, this is your x square. Right? This is your y is equal to x square. And from 1 to 2, this is your 1 and this is your 2. So this is the area which I just have found. This area I have found under the curve y is equal to x square between a and b. So this area is given by 7 by 3. Okay. So remember fx is positive, fx is above x-axis. If your fx is greater than equal to 0 and continuous on the interval a to b, then a to b fx dx gives you the area, gives the area under the curve. If fx is positive, it gives you the area. If it is negative, not guaranteed. Okay, so under the curve, y is equal to fx above the x-axis. Under the curve means we have to remain above x-axis and between the lines a and b, and between the lines x is equal to a and x is equal to b. So this gives you the area. So this, what does this mean? It means this gives you the area if your function is above x-axis. Then it gives you the area under the curve between the lines a and b, right, and above the x-axis. Okay, so that when we say area under the curve means automatically it means we remain above the x-axis and between the interval a to b. So that is the area basically which you get from integration. If your function is negative somewhere and positive somewhere between the points a and b, then it may not give you the area. Then the integral of this from a to c, this will be negative. If your function is negative, this integral is negative, and this integral from c to b fx dx, it will be a positive number. So if you add these two, you may end up getting 0. May, I'm not saying 0. It may be positive, it may be negative, it may be 0, anything. So you know that area cannot be negative, area cannot be 0. So you may not be using this if your fx is 0 somewhere. So what we do this thing. If fx is negative, let's say on some interval a to b, then area above, because now if fx is negative, it is down there, right? Now area between this and x, if you want to find this area, let's say if you want to find this area, right, this will be then the area between the curve y is equal to fx and the x-axis, right? Between, now we cannot say under the curve, it is above the curve now. So area between the curve y is equal to fx and x-axis, right, and still over the interval a to b, of course we are not going out of this interval, is given by a to b, and we take the absolute value, or you can say that we can take the negative sign with that, because the function is negative. So I will multiply a minus sign with that and then integrate. Why I am doing that? Because when I multiply this by a minus sign, this curve will come up here. Okay. If this is my fx, then minus fx is above and it's positive. And now if I integrate this positive function, it gives you this area, which is exactly the same as the below area, right? These both areas are the same. So we multiply it by a minus sign and then integrate. That gives me the area. So if my function is negative somewhere, let's say from a to c, it is below x-axis, and from c to b, it is positive, then I will integrate from, then this whole area will be equal to, from a to c, I will multiply my function by a negative number because it's below x-axis, and from c to b, I will integrate it directly without multiplying by a negative number. Okay, so this is the correction for this part. This is the correction for this part, and this part comes directly, no problem. Agree? So if your function is changing the sign within the interval, you have to break your integration at c. And before c, I'm not saying that if the integral is negative, you have to multiply. No, Means if a function is negative and positive somewhere and you integrate from a to b, you can do that, no problem. You can find this, no need to break it. You will get some answer, but that answer does not give you the area that I'm looking for. I will get an answer, but this is not the area, shaded area, which I have shaded on the left. Shaded area, this one. It does not give me this area. That's the only thing. So if they ask you what is the area, if they ask you this question, just find the answer. No problem. For example, if they ask integrate x square from integrate x cube from -1 to 1. If this is my question, I will not see that whether it's negative or positive. I will just take the integral and get the answer. It will be 1 by 4 and minus 1 by 4, which is 0. Right? That is the answer of the integral, no issues. If the question is find the integral, that is my correct answer. But does this give you the area? No. That is actually the issue. So if they ask you, this is my x cube, this is my x cube, sorry. This is my x cube, and if I am integrating this between -1 and 1, my answer is 0. But if they ask me what is the area, this whole area, now I cannot find this area using this integration, because you see integration cannot be 0. Area cannot be 0. So I will find this area separately and this area separately and then add. So I will call this area maybe A1. I will call this area A2. So these both areas will be added to get the answer. So the first area comes from -1 to 0, and I will multiply x cube by minus sign and integrate. And then I will go from 0 to 1 and integrate x cube directly. Okay. So now if you do that, it will become 1 by 4 plus 1 by 4. This will become your area. That is 2 by 4, 1 by 2 is the answer. You can do that. I did it directly, but if you do, you will see that the both will be 1 by 4. So this is the area actually. So the questions are different. If your function is somewhere negative, somewhere positive, we are not saying that you cannot integrate. Yes, you can integrate, get the answer. That is the answer to the integration. But if they ask you what is the area, then I cannot integrate it directly. Okay, so it based on the question which they are asking me. So see here, if a function is continuous on the interval, then f is integrable on AB, and the net area between the graph A and B is this one, right? The net signed area is the integration from A to B. We already know that. But if my function is becoming positive and negative somewhere, I have to be careful. Like that. You see here? So if I find the integration from 0 to 2, it's not a problem. I can do that. But if they ask me to find the area, then I will do them separately. I can do them separately. So these are the properties that I wrote, right? All the integration properties are coming with us. So where is the fundamental theorem of calculus? It is given in 5.6. So from 5.5, I only wrote the properties. So no need to do anything else. We can just go straight to 4.6. So see here in example 8, y is 1 minus x square, and you see from 0 to 2, from 0 to 2, it is positive from 0 to 1, and it is negative from 1 to 2. So you see they split it. From 0 to 1, I wrote the function directly. But from 1 to 2, I wrote it with negative sign. Same function with negative sign from 1 to 2 because it was a negative function in this interval. So area will be 2. If you integrate it directly, then answer will not be 2. That will be the answer of the integral, but it will not give you the area. So let's see if I go to the exercise. They wrote something about dummy area. What is the dummy variable? This variable, again, a note is here that integral from a to b, when you have a definite integral, then doesn't matter what you write here. The variable is a dummy variable. Okay, this variable, whatever you have, x, x, y, y, z, z, we call it a dummy. Dummy means not actual, it has no worth. You know, when you go to a mobile market, and because they cannot open a new set for you unless you buy it, they show you a dummy mobile which has the same weight, same, everything is the same, but it's a dummy, it's just a toy. You cannot use it, right? Just to give you the idea, you grab that dummy phone in your hand. So okay, this is the actual weight, actual size, everything is actual, right? So that is a dummy one. So what do we mean by that? We mean if you have an antiderivative, so whatever variable is here, you got the answer, because at the end you have to put the values a and b. So it doesn't matter if it was x or it was y or it was z or it was t. At the end it is replaced by b and a. So doesn't matter, both will be same. So it means if I write from a to b fx dx, it is the same as from a to b fu du or f z dz maybe. It's a dummy variable, or maybe ft dt. No difference between that. If the limits are not given, then we cannot change the variable on our own. If the question is in x, answer should be in x. Here, answer is a constant. So even if you change your name of the variable, you can do that, no issues. Uh, so here you see they gave you a question. Find the area under the curve. Y is equal to x cubed 2 to 3 e to the power 2x log of 2. So all these are okay. E to the power 2x, let's say exercise 9. 5.6 exercise 9. They give you find the area under the curve fx is equal to e to the power 2x, and the interval is given 0 to log of 2, right? So we know that exponential is always positive, it's never negative. Exponential function is always positive. So here your fx is greater than equal to 0, and definitely it's continuous as well, no break. From 0 to log of 2 or even any interval, exponential is always positive and a continuous function, right? So ex is always positive continuous, so no worry about that. So it means the area will be equal to integration from 0 to log of 2 fx dx. And we know that the integration of this is 1 over 2 e to the power 2x from 0 to log of 2. And if we put this log of 2 first, I will get e to the power 2 log of 2 minus half e to the power 0. E to the power 0 is 1, but this is 4. You can cancel e and log. We can cancel e and log, but they will not be cancelled like that. If you have e and log of x, e and log cancel, give you x back. But there is a 2 here. You cannot cancel because there is a 2 inside. So what you can do, you can send this to the power. You can write it as half e to the power log of 2 square. You can send this to the power, and half e to the power 0 is 1. Now you can cancel e and log because they are together. So you got e to the power 2 square, which is 4, and minus half. So 4 by 2 minus 1 by 2 is 3 by 2. So that's your area. So whenever you have e to the power log x, e log cancels. But if you have some number here and log x, you cannot cancel e and log. First send p to the power. You can write log x to the power p, and now you can cancel log and x, you get x to the power. Okay, remember you can do that. Even if it's a minus sign, e to the power minus log x, either you bring it down, you can write e to the power plus log x, right? If you bring it down, your minus will become plus. And now you can cancel e and log. So your answer will be 1 over x, like that. So that's how you can simplify e to the power log. These are simple problems. So we can, let's say, 20th, 0 to pi by 4 secant square theta. D theta. So this is the question number 20th on 5.6. 5.6 problem number 20. If you want to write the page is 373. This was also page 373. So we know that the integration of secant square theta is tangent theta. But I will not stop here. I will. What is the problem? You went out. So theta from 0 to pi by. So if you put pi by 4 inside, it becomes tangent pi by 4 minus tangent 0. So it becomes tangent pi by 4 is and tangent 0 is 0. So the answer is no. 19th problem, let's say sine theta from minus pi by 2 to pi by 2. From minus pi by 2 to pi by 2. Sine theta. Sine theta is somewhere negative, somewhere positive. You see, answer will become 0. But I don't care. The integral of sine theta is minus cos theta. And from minus pi by 2 to pi by 2. Because it's not a question about the area. It is a question about the integration. So no worries. We can put minus pi by 2, cosine pi by 2, and then minus cosine minus pi by 2. So this minus will become plus. So you know that cosine pi by 2 is 0, cosine minus pi by 2 is also 0. No, sorry. Yes. Cosine pi by 2 is 0. So the answer is 0 here. Both cosine 90 and cosine minus 90 are 0. So you see, the answer is 0. And we don't have to worry about that we need to split the interval. No, it's just the question about integration. So we did the integration, answer is 0, no problem. Answer can be 0. But if you look at the graph of sine is this, from minus pi by 2 to pi by 2, right? This is the answer. So your answer is 0 for the integral. But if they ask me what is the area, right, find this shaded area, then I will split this into two intervals. Then I will go from minus pi by 2 to 0 and make sign negative, and then from 0 to pi by 2 make it positive, if they ask me about the area. Otherwise, this is the answer. They only ask me the integration. All right. So I think that's it. Here, let's say the last one, 30 more. This is a good one. 31. 2x minus 1 to 1, 2x minus 1 dx. See here, it's a mod function, 2x minus 1 dx. I don't have any integration for the mod function. We know that the mod remains the same if your x is greater than 0, and it becomes minus when x becomes negative, right? We put negative. So here I cannot perform this integration directly. It means I have to decide where this inside function is positive and where it is negative. So let's see, 2x minus 1 is 0 at x is equal to 1 by 2. It means my function has a break at 1 by 2. Okay. Now before 1 by 2, it's negative. You see, if your x is less than 1 by 2, then 2x is less than 1. You see, 2x and 1. So if x is 2x is less than 1, it means x is less than 1 by 2. And 2x is greater than 1, it means x is greater than 1 by 2. So my function is changing at 1 by 2. At 1 by 2, it is negative before, right? 2x minus 1 is negative before and positive after that. So it means I will start from minus half and stop at 1 by 2. In this interval, this function is negative. So I will put a minus sign if I integrate that. And this function is positive. 2x minus 1 is positive from 1 by 2 to 1. So if I remove the mod, I don't need to put a minus sign. Again, it's not about the area. Here, my function is given the mod function. I cannot integrate the mod function. So I have to split it into two intervals where this function is negative. Because this function is negative at 1/2. 2x minus 1 is negative for x less than half. 2x minus 1 is positive for x plus half. That's why where it is negative, I put a negative sign, because mod function is always positive. Mod function is like that. So if my function is negative somewhere, I will multiply it by a minus sign to bring it up. But here, I don't need to put a minus sign. It is already positive. So now we can integrate. It becomes 1 minus 2x. This becomes 1 minus 2x because of the minus sign. So if I integrate, it becomes x minus 2x squared by 2 from minus 1 to half. And plus, this becomes 2x squared by 2 minus x from 1 by 2 to 1. So if mod function is given, you have to split it at the point where your function is changing its sign from positive to negative. Now, if you put 1/2, this 2 and 2 is gone. If you put 1/2, it is half minus half square. And when you put minus 1, it is minus 1 and minus minus plus minus 1 square. This is the first one. And then the second one. Again, 2 cancel. So if you put 1, it is 1 square minus 1. And then when you put half, it is half square minus half will become plus half. Now you can do that. Half plus half is 1, right? This 1 minus 1 cancelled. But this 1 is plus. This is 2. Agree? So this will become 2 and 1. Half plus half is 1. So 2 plus 1 is 3. And this is minus 1 by 4. 3 minus 1 by 4 you will get. You can put it in the calculator. So 11 by 4 is the answer. Check it in the calculator. All right, so I think that's pretty much it up to 5.6. So when we come back next week, I will continue. Remember, we studied integration by substitution. So next we will study substitution for definite integral. Can we use substitution if the limits are given? substitution for definite integral a to b f x dx, or how we can do that. Of course, we can use substitution, but it will be little different than the regular one. So using substitution for definite integral, we did substitution in 5.3, but now we will again do it for definite integral. I think it is section 5.8 or 9 maybe. All right, so that's pretty much it from my side. If you have any questions, you can ask. So I will save this and upload on Moodle along with the video as well. So let me stop the video recording.